So let us understand continuity of some particular functions. So this note is very important, which I am giving you right now. Okay, so the first one, a constant function is always continuous. A constant function is always continuous. For example, f of x is equal to 3. 3 is a constant. So it is continuous at any value of x belonging to real value. At any value of x belonging to real number. Okay, because for any real number, 3 will remain 3 only. So it is continuous. Constant function is continuous at any value of x belonging to real value. Second, an identity function is always continuous. Now, identity function is f of x is equal to x. It is always continuous at x is equal to r. Now, this one is an identity function. F of x is equal to x. So it is continuous at any value of x belonging to r. Third one, f of x is equal to modulus of x. Modulus function or absolute value function. Okay. So this function is continuous at any value of x which belongs to r. Okay. Let x be any number. It is continuous at any number. Fourth one, f of x is equal to greatest integer function of x. So this is continuous at any real value of x except the set of integers. Except the set of integers. Okay. Right. So this particular function, absolute greatest integer function, it is continuous at all decimal values. But then at integer value it is discontinuous. Fine. Just remember this. We'll solve one extra problem based on this later on. Why it is discontinuous at all integer values. A polynomial function. Polynomial function is generally an algebraic function. Okay. So f of x is equal to a0 x raised to n plus a1 x raised to n minus 1 plus a2 x raised to n minus 2, so on and so forth. So this is a polynomial function, algebraic function, x raised to n function. It is continuous at any real value of x. So this is an algebraic function. Next one, rational function. Okay. Rational function is algebraic function upon algebraic function. So it is continuous at any value of x belonging to real values. Any value of x belonging to real values. Okay. It will be discontinuous only at certain places. This rational function will be discontinuous only at certain places. For example, if g of x is equal to 3x minus 2. Okay. So equate 3x minus 2 to 0, you'll get x is equal to 2 by 3. Now, if you put x is equal to 2 by 3, the denominator turns out to be 0. So rational function will be not defined. Okay. So it is continuous at any real value of x except for that particular value where the denominator turns out to be 0. Where the denominator turns out to be 0. Okay. Next one. 7. F of x is equal to sin x. Okay. F of x is equal to cos x. F of x is equal to e raised to x. Right. So these functions are also continuous for any value of x belonging to real number. Sin x, cos x, e raised to x. Okay. So these functions, these are two trigonometric functions, and this is an exponential function. Don't take a raised to x, take e raised to x, Euler's constant. So these functions are continuous at any value of x belonging to real number. Okay, now let us understand some ITFs. F of x is equal to sin inverse x. F of x is equal to cos inverse x. So these are continuous only between -1 to 1. Okay, so if x is equal to 2, the above functions are discontinuous. So it is continuous only for the values between -1 and 1, including -1 and 1. F of x is equal to tan inverse x. F of x is equal to cot inverse x. So these are continuous at any real values of x. At any real values of x. Okay. And the last, f of x is equal to sec inverse x, or f of x is equal to cosec inverse x. So these are continuous at -infinity to -1, union 1 to infinity. Okay. So these 10 points you should remember. Let's go back to the exercise. Exercise 7a. Question number 1. Okay. Now f of x is equal to 2x square minus 1. We have to discuss the continuity at x is equal to 3. So there are two solutions for this. We have to discuss the continuous at x is equal to 3. Now if it is a one marker, solution number 1. If it is a one marker, you can straight away say that 2x square minus 1 is a polynomial function. So it is continuous at any real value of x. So it is continuous at x is equal to 3. It's a polynomial function. And if it is a two marker question, for this function, take LHL and RHL. Okay, at x is equal to 3. So 3 minus, then that H method you should do. And for RHL, it will be 3 plus. Okay. So by this, you have to prove the continuity. If it is a two marker. Fine. Question number 2. Examine the following functions for continuity. So these are, MCQ based. F of x is equal to x minus 5. So it's a polynomial function. It's a polynomial function. It is continuous at any real value of x. It is continuous at any real value of x. Second, f of x is equal to 1 upon x minus 5. And they have also given x is not equal to 5 because, the denominator will be 0. So this function is continuous at any real value of x. See, this is a rational function, f of x upon g of x. Okay, because this one is x raised to 0. So function of x upon function of x. So it's a rational function, but then it is discontinuous only at 5 because at 5 it turns out to be 0 denominator. So it's continuous at any real value of x. C part, f of x is equal to x square minus 25 x plus 5. Okay, x is not equal to minus 5. X is not equal to minus 5. So it is continuous at, this also is a rational function, f of x upon g of x. It is continuous at any real value of x except minus 5, because at minus 5 the denominator turns out to be 0. Okay. Then question number 2, Sub question D. Now it's an absolute value function, but then it is not modulus of x, it is modulus of x minus pi. So we'll rely on graph for this. Let us rely on graph. Let us take some sample value, x and y. Okay, when x is 0, so this is modulus of 0 minus pi, which is 5. When x is 1, 1 minus pi, which is 4. When x is 2, 2 minus pi, which is equal to 3. When x is 3, 3 minus pi, which is equal to 2. Minus 1, minus 1 minus pi, which is 6. Minus 2, minus 2 minus pi, which is 7. Minus 3. Minus 3 minus pi, which is 8. Okay. So some sample values we have taken. So let's make a graph of it. 0, 1, 2, 3, minus 3. Okay. So this is 0, 1, 2, 3, minus 1, minus 2, minus 3. Okay. So when x is equal to 0, this is 0. At 0, it is, sorry, when x is equal to 0, it is 5. 1, 2, 3, 4, 5. Oh, sorry, this is 5 over here. Okay. When x is equal to 1, it is 4. When x is equal to 2, it is 3. 3 will be 2. Okay. Then minus 1, 6. So for negative values, it is increasing. For minus 1, it is 6. Okay. So it is a decreasing trend. So for 4, 4 will be 1. You can calculate the value. For 5, it will be 0. So generally 5 is the critical value for this problem. 5 minus 5 is 0. Okay. For 6, 6 again it will be 1. So this will be the graph. Till 5 it is going to decrease, and then from 5 it will increase. Okay, so there is no break in the graph. There is no gap, no jump. So it is continuous at any real value of x. So by graph also you can explain this. The graph is continuous. There is no break, there is no jump, there is no gap. So it's continuous at any real value of x. Okay. Now let's go to exercise 7a. Question number 6. Find all the points of discontinuity. Find all the points of discontinuity of the function. Okay. So f of x is equal to 2x plus 3. X is less than or equal to 2. F of x is equal to 2x minus 3 when x is greater than 2. Okay. So we have to discuss the continuity at all real values of x. They have not mentioned a specific point. Until the previous session, they were mentioning the specific point. You have to discuss the continuity at 2 or 1 or 3 or something like that. Here they are not mentioning. But then 2 is the critical point because at 2 the changes are happening. Near to, on 2 the changes are happening in the function. So 2 is the critical point. So we will discuss the continuity at 3 places. At 2 because it is the critical point. For all the points uh, of where x is greater than 2, for all the points where x is less than 2. So these are 3 cases. So first part 1. Okay. To discuss continuity at x is equal to 2. So at x is equal to 2, you do all 3 things. LHL, limit x approaching 2 minus x less than 2, 2x plus 3. Solve this by H method. Then RHL, limit x approaching 2 plus x is greater than 2, 2x minus 3, then f of x equal to 2. Okay, x equal to 2 is 2x plus 3. So 2 into 2, 4 plus 3, which is 7. Okay, check these values also. If all three values are same, it is continuous at x is equal to 2. Fine. This was part 1. Part 2, we'll check over here. Okay, for x greater than 2, the function of x is 2x minus 3. So this is a polynomial function. So it is definitely continuous at any real value of x greater than 2. It is continuous at 3, it is continuous at 2.1, 2.2, 2.3, 4, 5, whatever. Let x be any real value with more than 2. Because the function is same. It is same. It is not changing. Okay, when you say for 2, the function changes. For 2 and very, very near to 2, the function changes. So 2 is the critical value. For that, you need to do LHL and RHL. But then x greater than 2, the function is same throughout. So it's so it's a polynomial function and it is continuous at any real value of x greater than 2. Same way, for x less than 2, f of x is equal to 2x plus 3. It's a polynomial function. Therefore, it is continuous at any real value of x less than 2. The function does not change. Okay. For example, if x is equal to 5, sorry, for x is equal to 0, the function will remain the same. It is not going to switch from one function to other function. And 0 is less than 1. Okay. And 0 is the real value. So it's continuous for x is equal to any real value which is less than 2. Okay. So it is continuous for 1.9, 1.8, 1.7, 1.5, 1, 0.5, 1, all values which are less than 2. Okay. Yeah. So whenever the point is not given in the problem, this should be your solution. Next one. 6. Sub question E. F of x is equal to x plus 5. X is less than or equal to 1. F of x is equal to x minus 5. X is greater than 1. So we need to find whether this function is continuous at all values. They have not mentioned at a particular value. So 1 being the critical point, we have to test at 1, doing properly LHL and RHL. And for x greater than 1, x less than 1, we have to write theoretically. So 3 parts to the problem. Part 1. So first part, we have to check the continuity at x equal to 1. So at x equal to 1, LHL equal to limit 1 minus, that is 1 x less than 1, that is x plus 5. Solve using h method. Let x is equal to 1 minus h, so on and so forth. RHL, limit x approaching 1 plus x greater than 1, x minus 5. Solve using h method. And the third thing, f of x equal to 1. So that is equal to x plus 5, 1 plus 5, which is equal to 6. So all three values should be same. Then only it will be continuous or discontinuous at x equal to 1. If it is same, continuous. If not same, discontinuous. Second part, this particular part. It's like the previous problem. For x greater than 1, okay, f of x is equal to x minus 5 is a polynomial function. Therefore, it is continuous at any real value of x greater than 1. For x less than 1, f of x is equal to x plus 5 is a polynomial function. Therefore, it is continuous at any value of x which is less than 1. Okay. So guys, if you see question number 7, and 7a and b both is of the similar category. We have to discuss the continuity at all points. They are not, considering a specific point. Yes, there is a critical value in the problem, but then apart from the critical value, you have to discuss the continuity everywhere. Okay. Let us go to the ninth problem, question number 9. Okay, so f of x is equal to -2, less than or equal to -1. F of x is equal to 2x. X lies between -1 and 1, and f of x is equal to 2. X is greater than 1. So there are two critical values over here. One is 1 and the other is -1. Okay. So we have to discuss the continuity at -1 and 1 separately. Okay. So there are 5 cases in this. At -1 and 1, you need to discuss the continuity. Then x less than -1, all these points, you need to discuss the continuity. In between all the points, x lies between -1 to 1. For this point, you need to discuss the continuity. And x greater than 1, you need to discuss the continuity. Okay. Now, for x equal to -1, you have to do LHL and RHL. So LHL, limit x approaching 1 minus x less than 1, -1, sorry, -1 minus, -1 minus, and x less than -1, which is -2. Okay. So here you can do, it's a limit of a constant, so it is directly a constant. Okay, there is no x term over here. -1 plus x greater than -1, so that is 2x. Now here here you need to do h method in the RHL because x is there. So let x is equal to -1 plus h. So h will approach 0. 2 into -1 plus h. Okay. So 2 into -1 plus 0, which is -2. Okay. And the third thing, f of x equal to -1. X equal to -1 is also -2. So here all three things are same. LHL equal to RHL equal to f of x equal to -1. Therefore, the function is continuous. Therefore, the function is continuous at x equal to -1. Similarly, you need to do for x is equal to 1. For x is equal to 1, 1 is a critical value. At 1, there are changes happening. Okay, the function is changing. So you need to do LHL, RHL, and f of x equal to 1 for this and check whether the value is same. Okay. So that's how you will conclude with the continuity for x equal to 1. Now I'll discuss the continuity of the other values which are remaining in the problem. Okay. The reasoning should be correct. Should give proper reasoning. So just wait. Third part. For values of x less than -1, f of x is equal to -2 is a constant function this time. And constant functions are always continuous for any real value of x. Therefore, it is continuous at any real value of x less than -1. Okay. So this part is also done. Let's focus on this part. x greater than 1. For x greater than 1, f of x is equal to plus 2 is a constant function. 2 is a constant. Therefore, it is continuous at any real value of x greater than 1. Okay. And the last part, the middle part, for values between -1 and 1. So between -1 and 1, I'll take a new slide. Between -1 and 1, that is x between -1 and 1, f of x is equal to 2x. Again, it's a polynomial function, algebraic function, polynomial function. Therefore, it is continuous at any real value of x between -1 and 1. Okay. So this is how your solution should be. Fine. Let's go to question number 10. Question number 10. F of x is equal to x cos 1 upon x. Okay. This is when x is not equal to 0. And f of x is equal to 0 when x is equal to 0. See, look at this notation. This is the value of x. So when x is equal to 0, f of x is equal to this 0. Fine. Understand this notations. Within the bracket, this is x. Okay, this is x. Outside the bracket, equal to k right hand side way, this is the value of f of x. So now we need to discuss the continuity at x equal to 0. Okay, at only one point, at 0. So this is less than, this is not equal to, so this is greater than 0, this is less than 0. So first I will start with LHL, limit x approaching 0 minus x less than 0, x into cos 1 upon x, x into cos 1 upon x. Let x is equal to 0 minus h. As x approaches 0, h will also approach 0. Okay, so this will be limit h approaching 0, 0 minus h, cos 1 upon 0 minus h. Limit minus h into cos minus 1 upon h. Okay. See, now x is not exactly equal to 0, but then very near to 0. Okay, now understand this solution. Cos of any trigonometric function. Cos of, sorry, I said it very wrong. Cos of any angle. Cos of any angle. Cos of any angle. Within the bracket, let it be any angle. So sine and cos of any angle lies between -1 to 1. Okay. This value, the pink colored value, it lies between -1 to 1. Okay. But then this h is 0. So 0 into any value will be 0. So LHL is equal to 0. So this was the trickiest part. The trigonometric function cos of any angle lies between -1 to 1. Now that value into this 0 comes from this h, gives me 0. Okay. Similarly, we have to start with RHL. So RHL, x approaching 0 plus x is greater than 0. The function remains same. Cos of x into 1 by x. Let x is equal to 0 plus h. As x approaches 0, h will also approach 0. So this is equal to limit h approaching 0, 0 plus h, cos of 1 by 0 plus h cos into 1 by h. Same logic. This h is 0 and this cos of any angle lies between -1 to 1. So 0 into this will be 0. So LHL equal to RHL. And the third thing is what? F of x equal to 0, which is 0. This is also given in the problem. So all three things are equal. All three things are equal. Therefore, it is continuous at x is equal to 0. Okay. Similarly, if the same problem is asked for sine, instead of cos, the question is for sine. Okay, the solution remains same. For sine also, all values will lie between -1 to 1. They will ask you questions related to sine and cos only for this kind of problems. Okay. Question number 11. Question number 11. F of x is equal to x minus a cos of 1 upon x minus a. And f of x is equal to 0 when x is equal to a. This is not equal to a, this is equal to a. So this implies both x is greater than a, x is less than a. Okay. Again, LHL. Limit x approaching 0 minus is x less than 0. F of x. F of x is x minus a cos 1 upon x minus a. Let x is equal to 0 minus h. As x approaches 0, h will also approach 0. Okay. So this will be limit h approaches 0. X is 0 minus h into cos of 1 upon, right? So see, we are left with this limit h approaching 0 minus h minus a cos of minus h minus a. Right? I think somewhere something I've written wrong. Yeah. Sorry. It's not 0, it's a. The problem is for a. I wrote 0 over here. So a minus and a. So a minus h, x approaches a, h approaches 0. Yeah. So this is a minus h, a minus h. So a gone, 1 upon minus h. Fine. Here also a gone. So we are left with minus h. By mistake, I had written 0. It should be x approaching a now. I had written 0. Now see, put h as 0. Now this value, cos of any angle lies between -1 to 1. So 0 into this will be 0. Clear? Similarly, you have to do for RHL. For RHL, you have to write x plus a. Sorry, a plus. This particular value will be a plus. Okay, this will be greater than. This will be a plus. This will be the same. Okay, so here it will be a plus, a plus. This is plus, this is plus, and this is plus. Remaining solution remains the same. So LHL equal to 0, RHL will be 0. At x equal to a, f of x equal to a is also 0. All three things are same. Therefore, the function is continuous at x is equal to a. Clear? Yeah. Just a second. One or two extra problems I'm doing right now. Please wait. Yeah. So the question is, f of x is equal to 2x minus modulus of x. We need to discuss the continuity at x equal to 0. So we need to find out whether the function is continuous at x equal to 0. So LHL, only this much amount of information is given. By the way, this is solved example number 7 from the textbook. Limit x approaching 0 minus x less than 0. 2x minus modulus of x. Okay, let x is equal to 0 minus h. As x approaches 0, h will also approach 0. So this is equal to limit h approaching 0, 2 into 0 minus h minus modulus of 0 minus h. Okay, so 2 into minus h, modulus of minus h, minus 2h, minus h, because modulus of minus h is h. So first simplify totally and then put the value of h as 0. So this is equal to 0. Okay, now RHL, this will be plus, this will be plus, this will be greater than, okay, this and this will be plus, this and this again it will be plus, this will be plus. Okay, so 2h minus h will be, this time it will be h, so the answer will be 0 for RHL. So LHL equal to RHL, therefore, the function is continuous at x is equal to 0. Solved example number 8. They have given g of x, so I'll just write f of x. X minus greatest integer function of x. Greatest integer function of x, okay? So we need to find out where it is continuous. Or rather they have said, show that the function is discontinuous at all integral values, where x denotes the greatest integer less than or equal to function. Right? Now see, LHL. Now this is a bit tricky than the previous one. LHL, limit x approaching. So this has to be proved continuous at x equal to any integer value. So let's for example take x is equal to 2. As an example we are taking. We can do that in exam. 2 is an integer, so we are just assuming to find out whether it is continuous or discontinuous at integral points. So that is integer value. So 2 minus, as an example, I'm taking 2. You can do that. X less than 2. So x minus greatest integer function of x. So let x is equal to 2 minus h. As x approaches 2, h will approach 0. Now be very attentive. Limit h approaches 0, 2 minus h, box of 2 minus h. Okay. Now see guys, limit h approaching towards 2 minus h. This is going to be 1. I'll tell you why. Now this is 1 and this is 2. Okay. H is a very small value. 0.0001, something like that. H is a very small value. So what is 2 minus 0.00001? Something like this. Okay. So this is going to be box of 1.9999. So that value is over here before 2. So the greatest integer function tells that the previous integer has to be taken. The previous integer has to be taken. So instead of taking the answer as 2 for this, the answer for this will be 1. So 2 minus h, we are subtracting a smaller value from 2. We are subtracting a smaller value from 2. So it becomes 1.99999. So the greatest integer of 1.9999 is 1. Okay. So now see this. I hope you understood the reasoning over here. Okay. Now 2 minus h is 1. And I need not put a box over here because we calculated the answer. Okay. So this will be 1 minus h, 1 minus 0, which is 1. Okay. Now we'll also calculate the RHL over here. RHL, limit x approaching 2 plus. For example, we are taking 2. Okay. Let x is equal to 2 plus h. In the problem, you can take as an example 3, 4, anything negative number also you can take. 0 also you can take. But then For safety side, you can take positive integer. As x approaches 2, h will approach 0. Okay, x minus box of x. So 2 plus h minus 2 plus h. Now 2 plus h is a very small value added to 2. So if that value is added to 2, it will become 2.0001. So this is 2 and this is 3. This is 2.001, something like that after 2. So greatest integer of that will be the integer which is to the left. So the answer is 2. So the answer of this is 2. So limit h approaching towards 0, 2 plus h minus 2. 2 gone. So the answer is 0. So LHL is not equal to RHL in this case. RHL is not equal to RHL. Hence it is not continuous at an integer value. And that's what we had written in the this thing also. Properties also. It is continuous at any real value except the integers. It is continuous at all decimal values also, but then not integers. Okay. Then you can solve example number 35 on your own. Example number 35, okay, for practice. Okay, so it is based on the same logic. Please solve it for your exam. Okay, that completes the continuity part. In the next part, we'll be starting with differentiability.